In this module, we'll start working with electron configurations, which is just the continuation of what we were doing in the last module, but I don't know, in a slightly different way that is less weird and more methodical and hopefully a little more helpful. So we will employ this last quantum number, that spin quantum number. We are going to put the orbitals in order of their energies. Then we're going to talk about how to put electrons in the orbitals, and there are, I don't know, hopefully you think this is a good thing. There are rules that let us do that in a specific way. And then we're going to go into writing basic electron configurations, which an electron configuration is just a listing of every orbital that tells how many electrons are in the orbitals. Okay, so each orbital can hold 2 electrons, and this last quantum number, m sub s, differentiates those 2 electrons. So we call it the spin quantum number because it represents the spin of the electron, and this is a plus 1/2 or a minus 1/2, which we just call spin up or spin down. So plus is up, minus is down. And when we put it into a picture of what the orbital electron configuration looks like, we will just do an up arrow or a down arrow. Now, the first set of arrows that I've drawn, that we call it like a single-headed arrow, this is the most technically correct way to draw it and will help you remember your conventions when you get into organic chemistry and start pushing electrons. However, you will see, and I will accept, just a regular up arrow or a regular down arrow. If that's where you want to start, that's totally fine. Okay, so before we put in the electrons into the orbitals, we're going to order them in their energy orders. So this energy ordering of the orbitals, these are the Schrodinger results. So this is a result of that Schrodinger equation where we were applying the Hamiltonian operator. We got an energy value out of it. The initial ordering is based on n. So n equals 1, lowest energy. N equals 2 comes after that, going up, and then n equals 3, just like we saw in the Bohr atom. Within a level, the s orbital has a lower energy than the set of 3 p orbitals, and the p orbitals have a lower energy than the set of 5 d orbitals, then the f orbitals, and so on. So I've got a picture here of this like final version of this like general energy level diagram, where at the very bottom we have just the one s orbital. N equals 1, we only have the s orbital. We refer to that specific s orbital, so with the quantum number in the front and then the letter, no space. So 1s, lowest energy. The next quantum number is 2, principal quantum number. In the n equals 2 level, right, we had s orbitals, well, an s orbital and p orbitals. So the 2s is lower than the 2p. And I have that highlighted here in green. In the n equals 3 level, we have 3s, then 3p, and then 3d. And then this is where things start to get just a little bit complicated. So remember from the Bohr model that the energy levels get closer together as you go up in energy, which means that sometimes our levels start to overlap. We're going to have some straightforward ways to cope with this fact, but right, I've got my 3s, 3p, 3d in their nice energy order, but my 4s, it's still higher than some of the n equals 3 levels, but my 4s has a lower energy than my 3d set of orbitals. 4p is higher than 3d, and then my 4d orbitals go up. But then when I get to n equals 5, my 5s is lower than my 4d. Now this matters because of how we're going to put electrons into the orbitals, but again, we will have straightforward ways to deal with this fact, but the sort of overall effect and final answer is that it's mostly in order of first base it on the principal quantum number, then S is lower than P, which is lower than D, which is lower than F, with some squishiness as we get to higher energy. So the guidelines for filling orbitals, these are rules that we're going to use. I guess I stopped calling them rules because only one is a rule, the other two are principles. The first is the Pauli exclusion principle, which is that no two electrons in an atom can have the same 4 quantum numbers. So a set of 4 quantum numbers will give you essentially the address of an atom. It'll tell you the N, which is the energy level that it's in. The L will tell you the shape of the orbital that it's in. The M sub L will tell you which specific orbital in that set. And then each orbital can hold 2 electrons. So N, L, and M sub L are like the beginnings of an address to an apartment where 2 people live. And within that apartment, you can uniquely identify the 2 people, and we do that for electrons with that spin quantum number. The second principle is the Aufbau principle, which is, this is a German word that means something like building up. It just means that you start at the lowest energy and go up from there. So you will always fill from the bottom and move up. You won't skip any spaces as you're going. The last thing that you need, which is actually a rule, is Hund's rule, which says that electrons don't pair up unless they have to. So when you're filling something like p orbitals, right, when you fill an s orbital, there's only one in the set. I don't know, we've got air quotes on a set in a pre-recorded video, which is a new level of thing to deal with, I guess. We don't have to worry about it for s orbitals, so that if you're going to put 2 in there, they have to be paired up because there's only one. For p orbitals and d and f, they don't pair unless they have to. So if I'm putting electrons into this set of p orbitals, I'm going to put each one in its own orbital until I can't anymore. And then I will start to pair up the electrons. Of course, we'll do examples. This was always taught to me as like the school bus rule, which was that like when kids get on a school bus, they don't sit with anybody else unless they have to, because everybody wants to have their own big seat. And so electrons want to do the same thing. So what we're using with this rule is that this idea that to a first approximation, orbitals in a subshell, so like all of the 3p orbitals, and I mean that like principal quantum number 3, so 3p, those 3 total in the subset p orbitals all have the same energy. And the word that we use to mean that they have the same energy is degenerate. So we would say that the orbitals, the 3p orbitals are degenerate. All right, some examples. And we'll start with hydrogen. So hydrogen, atomic number 1. So it has 1 electron. That 1 electron will go in the lowest energy orbital, which is the 1s orbital. And what I have drawn here is an orbital diagram. So if I ask you for an orbital diagram, what I mean is I want you to draw the line, label the orbital underneath, and then put the electron or electrons in it. So I've got 1 electron in here. It's not technically wrong to make that electron spin down, but by convention, we start by putting them spin up. So this is the orbital diagram, the line that represents the orbital, the, the label of the principal quantum number and shape of the orbital that that electron is in, and the arrow representing the electron. Now, if I wanted to assign quantum numbers to this electron, it's in a 1s orbital, so n is 1, L is 0. There's only one orbital in the set of s orbitals, so the m sub L is also 0. And then I have drawn an up arrow, so my spin quantum number is plus 1/2. The electron configuration, so this is where we just write out from left to right the orbital with the number of electrons. So I'm going to write 1s, which is the orbital that this electron is in. And then I'm going to do a superscript 1 because there's one electron in that 1s orbital. Okay, let's get a little more complicated, so this will make maybe more sense. For helium, I have 2 electrons. I am starting at the lowest energy, so I have a 1s orbital that I can put electrons in. I put in my first electron, spin up, and then this orbital can hold 2 electrons. I can't go up in energy until I've filled this, so I'm going to put my second electron in here. So my orbital diagram is the line with 1s underneath it, and my 2 electrons pointed in opposite directions. Let's write out the quantum numbers for these to show that we didn't mess up the Pauli exclusion principle, because it's going to look early on kind of like we did. So I've got these labeled. The spin up, or the up arrow, is electron A. The other one is electron B. For electron A, I'm in a 1s, so I've got n equals 1, L equals 0, m sub L equals 0. Well, electron B is also in a 1s orbital. N equals 1, L equals 0, m sub L equals 0. But making them point in different directions is what gives me that differentiation between them. So m sub s is plus 1/2 for electron A because it's pointing up. M sub s is minus 1/2 for electron B because it's pointing down. This is how we know we've met the Pauli exclusion principle. My electron configuration, which I guess I've already written, but we kind of skipped past it. The electron configuration, I have a 1s orbital with 2 electrons in it. So I've got 1s and then a superscript 2. Okay. Let's jump to carbon. Carbon has 6 electrons. So I'm going to set up my orbitals in terms of energy, because I'm going to need to go beyond the 1s orbital. So I've got 1s as my lowest energy. The next highest up in energy is 2s, then the 2p, and then the 3s. So let's fill this in. I don't know if we might need more. We might not use all of this, but let's try this. So starting at the bottom and building up, I'm going to put 2 electrons in the 1s, right? I've got spin up, spin down. That whole energy level is filled, so I'm going to go up to the next subset that I have, which is the 2s. I can put 2 electrons here, right? So I'm fulfilling my Aufbau and Pauli exclusion. I've used up 4 electrons. I have 2 left, and I get to the 2p orbitals. So I have 3 open orbitals. I could hold a total of 6 electrons, because each can hold 2, but I only have 2 total to put in. So I'm going to put them in separate orbitals, right? They will not pair up unless they have to. So they will both go in their own orbital, and they both have to point the same direction. So this is Hund's rule. This is they don't pair up until they have to, and then I am adding the inclusion and reminder that they should point in the same direction. Now the electron configuration for this is we write the orbital with the superscript for the number of electrons. So 1s2, then the next up in energy is 2s with 2 electrons. When we get to things like P and D and F, we just write 2p in this example, and then the total number of electrons in that level. We don't show any kind of differentiation in the electron configuration like we do in the orbital diagram. So we would just write 2p2. Let's do a bigger example again together. We're going to write the electron configuration and orbital diagram for sodium. So find sodium on the periodic table. It has 11 electrons. I am going to start by just writing out the orbitals in order. And, I will probably end up one short, a couple too many. You can always erase them. You can always add as you're going. So I'm also going to do this instead of bottom to top, which takes up a ton of vertical space when you write it. I'm going to do it left to right. This is a totally acceptable way to do this, where lowest energy is on the left, higher energy on the right. And if you would like to do it this way, you can. You'll have a lot more space to do your work if you do it left to right. If you prefer to do it vertically, that's also fine. You're not required to, though. So I've got 1s, 2s, the 3 together that are the 2p orbitals, 3s, and then I'm going to go ahead and put 3p on here, and we'll see what we use. So since lowest energy is on the left, I'm now going to fill from left to right. So, right, instead of filling bottom to top, I'm going to fill left to right. So still lowest energy to highest energy, and start by putting 2 electrons in my 1s, 2 electrons in my 2s. I have at least 4. When I fill these in, I'm going to go unpaired, 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 and then go back and pair my electrons. Just in case, as I'm counting, I end up with something unpaired, I'm not going to have to erase and redo it. So 1, 2, 3, then 4, 5, 6 electrons in that 2p. So I have used 2, 4, 6, 8, 10 electrons total. I only have 1 left, and that 1 is going to go into the 3s. So I didn't need my 3p written out. My electron configuration, so that was the orbital diagram. Electron configuration, again, reading left to right, my 1s orbital has 2 electrons. My 2s orbital has 2 electrons. My 2p orbital has 6 electrons, and my 3s orbital has 1 electron.